Yolo-World is a zero-shot open vocabulary model based on YOLO v8.
This means that rather than only being able to detect one of the classes you've pre-selected and trained on, like the traditional models, Yolo-World can take any text as input for what you want to detect. Yolo-World uses an open vocabulary detection method, which leverages a text encoder, CLIP, published by OpenAI, to encode the noun phrases extracted from the input text into embeddings. An embedding is a way we can store multi-dimensional numerical data in place of words, capturing semantic meaning like parts of speech, color, size, shape, type of object, type of action, and much more, in numbers, which work more easily in machine learning models. Each word is represented as a vector, and words with similar semantic meaning would have closer proximity. So, dog might be close to wolf, skiing might be closest to snowboarding, but also relatively close to basketball and soccer because they're all sports, and funny might be close to humorous. The proximity can be measured with cosine similarity, taking the cosine of the angle between the two vectors. Embedding representations are more effective and efficient than one-hot encoding, which stores a 1 for the word in question and a 0 for everything else, and that gets pretty sparse. It's common that embeddings are used in LLM-based models. CLIP takes in image-text pairs and computes a dense cosine similarity matrix between all image-text combinations, maximizing the similarity between the correct pairs and minimizing the similarity for incorrect pairs using symmetric cross-entropy loss. Models other than Yolo-World were having trouble keeping up in real time as they're using large computational detectors or an online text encoder. You can imagine with robots and autonomous systems, if you run too slowly and you miss a detection, what might happen. To improve efficiency during inference, Yolo-World added RepVLPAN, which connects text and image features by taking in reparameterized text embeddings and allows the encoder to be run offline. The prompt-then-to-text strategy encodes a custom prompt in offline vocabulary embeddings. Then the detector can infer on the fly without needing to re-encode. RepVLPAN also takes in the multi-scale image features from the YOLO v8 backbone and neck, which we talked about earlier. The RepVLPAN really helps fuse the image features and text embeddings. With the feature pyramids with multi-scale image features used in YOLO v8, it adds a text-guided CSP layer and image pooling attention to further enhance the interaction between image features and text features. Attention is all you need. The attention mechanism used in the transformer, created by a Google research team, has really revolutionized sequential algorithms like LLMs, influencing what many know AI to be today. It's mathematically allowed the algorithm to find which components of a series you should draw attention to more, or are more important to learn some connections with another series. It does this by computing 3 weight vectors for each, the query, key, and values. The output becomes a weighted sum of the values, and the weight for each value is computed by the compatibility function of the query and the corresponding key. There are a few variations of attention, like the scale dot product attention. When you take the dot product of 2 matrices, you find the similarities, as higher similarities have higher values, and lower similarities have lower values. In the RepVLPAN, the text-guided CSP layer injects language information into image features, with the max sigmoid attention after the last dark bottleneck block. Max pooling extracts the most important features from the text, and sigmoid scaling squashes the features between 0 and 1, making them better suited for weighting other features. The weighted text features are applied to the image features, making them more aligned with the semantic context provided by the text. The image pooling attention, on the other hand, enhances the text embeddings with image-aware information. After feature maps are created, attention weights are computed to know where focus should be given within the feature maps, and the weights are used to pool the features, enhancing those that are more important and diminishing those that aren't. Finally, we have the box head, which helps find bounding boxes through regression, and the text contrastive head, which looks for object-text similarity by leveraging the L2 norm and affine transformation to help stabilize the region text training. In the pre-training step, rather than having the label data be just bounding boxes and category labels, they use region text pairs. So the region is now connected to a text, which can be a category name, a noun phrase, or an object description. So we have images and texts as inputs and the predicted bounding boxes as outputs, along with the corresponding object embeddings. During training, they use the mosaic technique where 4 images are overlaid onto one image used to train, where there's a list of all positive nouns associated between all the images and a random selection of negative nouns, or things that aren't there, totaling up to 80 between the two.
Pretty early on, I learned that machine learning models are only about as good as their data. So I got curious.
What data did they use to train CLIP? Clip says they trained using 400 million image-text pairs collected from the internet in a dataset they called WIT, or Wikipedia-based image text. They used Wikipedia to curate a dataset with 37.6 million entity-rich image text examples with 11.5 million unique images across 108 Wikipedia languages.
If you'd like to see where I implement this algorithm and others, check out the Bathroom Terror Detector, and don't forget to subscribe for more.